Everyone, in this video we're going to go through binary and permutation matrices. So two words that you might not be familiar with. You might have heard binary before, especially if you're into coding, and permutation you may have heard before, but probably a little bit more complicated than just what a binary matrix is. So let's quickly go through what a binary matrix is, and then we'll focus mostly on permutation matrices for this video. So a binary matrix is just a matrix where all your elements are either a 0 or a 1. All right, that's as simple as it is. And we've already seen one type of binary matrix, that's the identity matrix. So remember, your identity matrix has ones going down the diagonal, can be of any size, just has to be a square matrix. So this one's a 3 by 3. All right, so that's your identity matrix, which we've looked at before. And remember, your identity matrix is the same as multiplying a matrix by 1, so it doesn't change the matrix at all. Now, a permutation matrix is a special kind of binary matrix, like the identity matrix is a special kind of binary matrix. The identity matrix is also a permutation matrix, and I'll explain why in a second. So a permutation matrix has to be a square matrix. It's also a binary matrix, so we only see zeros and ones. But what makes it special is that each row and column must contain the number 1 only once. All right, so it should only have the number 1 only once. So we've got two examples here. So we've got a binary matrix, so we can clearly see there's just zeros and ones in that matrix. It's also a 3 by 4 matrix, so it can't be a permutation matrix because it's not a square matrix. It also has more than one in each row and column. So if we have a look at the permutation matrix, it's a 4 by 4 matrix, 4 rows, 4 columns, and the number 1 only occurs once in each row and column. All right, so that's what a permutation matrix is. And an identity matrix is also a permutation matrix because we also have the number 1 only occurring once in each row and column. Now, before we go too much further into what permutation matrices are, I'm just going to show you on your calculator. So I've just drawn this earlier because I thought it takes so long to do matrices on the calculator. So here we've got the identity matrix, and I'm going to multiply that by a 3 by 1 matrix, and I'm going to call this 1, 2, 3. Now we know that multiplying it by its identity matrix shouldn't change the matrix at all, so I should still get 1, 2, 3. Doesn't matter what I put in here, so I could have, sometimes you can use letters, B, C. All right, it stays in the same position. So remember, your identity matrix doesn't change. If I was to do it down here, if I was to do it as a row matrix, I would just have to do it before, because remember, when you're multiplying, the order matters. So if I did 1, 2, 3, I'm still going to end up with the same row matrix. Now with a permutation matrix, they're not all going to be identity matrices. You might have a 1 in the diagonal, and that just means the number doesn't change position. But let's say we're going to switch it up a little bit. So let's put a 1 there. So that means this now has to become a 0. Let's move this 1, so I'll make that a 0 over here, and we will put the 1 here. All right, so we still have a 1 in each row in each column, but it now won't keep the matrix the same. So let's go back and do our column matrix first. So I'm just going to copy that and paste it down here. All right, see how it switched the positions, and we're going to go through how those elements change positions. And if we did it with our row matrix up here, oops, did I not do copy? Just copy, please. All right, and then paste. All right, and it changes as well. All right, so if you've got a 1 along the diagonal, or if you had all ones along the diagonal, it doesn't change, but if you had a 1 anywhere on the diagonal, it also means that a certain element doesn't change, but we'll go through that in a sec. So that's what a permutation matrix is. It just changes the matrix, and we just did row and column matrices, but you can have more. So if we just take, actually what I might do is, let's do a 2 by 3, and so you can do any size as long as the multiplication exists, so it still switches. But what was I going to say? Your order does matter, and your permutation matrix does have to be a square, but what you're multiplying it by doesn't have to be a square matrix. You just have to, the multiplication just has to be defined. So let's have a look first of all. Actually, before we do, let's just have a look at this consider part. All right, so with your permutation matrices, whether you do it before, so that's what it means by pre-multiplied, or whether you do it after the matrix, which is post-multiplied, it actually will change either your columns or your rows. So that's important to know. Okay, so depending on whether your permutation matrix is first or whether it's after the other matrix. So if we have a look at this one, our permutation matrix is being coming last. It's post-multiplied, or it's to the right. And whereas this one, it was pre-multiplied. All right, so this matrix was being pre-multiplied by our permutation matrix. All right, so if we have the permutation matrix second or after, or it's being post-multiplied, or you can call it to the right, whatever, or we can just do an example. So here's matrix Q, and it's being multiplied by our permutation matrix. All right, that's what it means by coming second or to the right or being post-multiplied, and it will result in a column permutation. So what that actually means is it's changing the elements in the column. In columns. All right, and then the second one is basically the opposite. So if we had the permutation matrix first and it's multiplying another matrix, all right, that means it is pre-multiplied, or to the left or first, whatever language you want to use, just making sure that you know that it comes first. All right, and that results in a row permutation. So we're focusing on changing the elements in the rows as opposed to the columns. This will make more sense as we work through these questions, but the whole reason I'm doing this video is because it can be very confusing. All right, so let's first look at column permutation. So when applying a column, sorry, my dog's just barking at the birds. When applying a column permutation, the permutation matrix P must be a square matrix. All right, always has to be a square matrix where the row and columns are equal to the number of columns of matrix Q. So I kind of mentioned that before. So the columns of matrix Q, that's the matrix that's being multiplied by our permutation matrix. So here we've got 1, 2, 3 columns. That's why our permutation matrix is a 3 by 3. All right, so we've got to remember that. Matrix P contains 1 element in the following positions. All right, so we've got P1, 3. So that means row 1, column 3, which is there. P2, so row 2, column 1, which is there, and P3, 2, row 3, column 2. All right, so remember that notation we use to label the elements. Now this is how the permutation changes. So P1, 3, so that position, the one in that position, indicates that column 1 in matrix Q. So let's just have a look at what's happening here. I'm going to get rid of all this so I can highlight it again. All right. So indicates that column 1 in matrix Q, 3 and 4, all right, will become column 3. So in our permutation matrix, it was in column 1, all right, but because of this 3, all right, so our 1 in column 3, it's now being switched to column 3. It's about to write 3/4 as my dog just walks past me. All right, 3 over 4. Not 3 over 4, 3 and 4. All right, let's do it in a different color for the next one. So P21 indicates that column 2 in matrix Q, so the 7 and the 1, will become column 1. All right, so here we go, column 1, 7, 1. And then lastly, we've got P32. So this is this one here. Indicates that column 3 in matrix Q, so the 2 and the 5, will become column 2. So it's just switching. Now, if you need to, you can always check your answer on your calculator. So let's have a quick, just putting this in. Now this is very similar, so I might just drag that down. So 3, 7, 1, 2, 5. And then we've got, just change this around. It'd be good if I did it the same, but I didn't plan on doing this. All right. And then you can see, just move this out of the way. All right, that's how it changes. You can keep going and changing your permutation matrix. So if we did this matrix by this one, all right, it changes it the same way. And then if we did it one more time, just going to move this over here. Right, we end up with our original one. So that's important to note, but that's something we're going to explore later because we're just going through the basics right now. All right, so let's have a look at this example here. So perform a column permutation of matrix X by using the permutation matrix P. So here we've got letters instead of numbers, and often you will see that being used in an exam, or it could be used on your SAC. So you do have to understand how they change, because sometimes you can't just do it on your calculator. All right, so step 1, start by determining the movement of each column in matrix X by using matrix P. All right, so let's put in, I'm going to go back to blue. Let's put in the elements. So we've got P, so we're going to start off with this row 1, and we're in column 3. So that means column 1 moves to column 3. So maybe we can do it as we go. Actually, I'm going to put the answer down here. All right, so the matrix will be the same. So what I mean by the same, it's still going to be a 1 by 4. So this is a 1 by 4. So your product matrix will also be a 1 by 4. So this number here means that the number, or the letter in this case, in column 1 is now going to move to column 3. So that U is now going to be there. All right, moving to the next one. So we've got this one here in row 2, column 4. So it's going to go from column 2 to column 4. So our letter in column 2 is M, and that's going to go to 4. All right, then we've got the next one. So row 3, column 2. So column 3 moves to column 2. So column 3, we have the letter L. That's now going to be in position 2, or column 2, I should say. And then lastly, we've got row 4, 1, and, well, we've only got one spot left, but we can just see that. So P is in position 4, now moves to position 1. So we get the word plum, which is pretty cool. Oops, I should fill this in. So column 4 moves to column 1. Now, if we were to do that again, all right, we do still change the position, so based on what we've got written here, but instead of having these letters, we have PLUM, and we apply the same transformation to them. All right, let's have a look at row permutation. So make sure I would put this definitely in your bound book, all right, as an example to have to understand how they switch. All right, row permutation. So when applying a row permutation, the permutation matrix P must be a square matrix. So all permutation matrices are square matrices where the number of rows and columns in P are equal to the number of rows in matrix Q. All right, so this matrix Q, we've got 1, 2, 3, 4 rows and 3 columns. So this 4 here tells us that my permutation matrix has to be a 4 by 4. First of all, it has to have the same number of columns, but because P is a square matrix, that's why you get 4 by 4. Okie dokie. So, in this previous example, we just had a row matrix. Here, we've got a 4 by 3 matrix that's going to be changed. So, it's not just one element that's changing, it's multiple elements in the row. All right, so let's have a look. We've got my highlighter, good. So matrix P contains one element in the following position. So remember, we only have the number 1 occurring once in each row and each column. So here is in row 1, column 4. So that indicates that row 4 will now become row 1. All right, so see how it's switched in a way. So here we read it as column 1 went to column 3. Now we're just going to do the opposite. Row 4 goes to row 1. So in row 4 we have JKL. Let me just put the answer in here. So JKL was in row 4, now it's in row 1. So JKL. All right, then we have a 1 here. And remember, when it's on the diagonal, it actually doesn't change. So P22, so the number of the row and the column number are the same. So that indicates that row 2 will stay at row 2. So row 2 is DEF. So DEF. All right, then we've got 3, 1. So indicates that row 1 now becomes row 3. So row 1, which is ABC, now becomes row 3, ABC. So see how it's a whole row that's changing? And then 4, 3, so the last one we have to do is row 3 now becomes row 4. So JKL. Now, let's see if we can actually do that in our calculator. So let's quickly do that. Sometimes the calculator doesn't like letters. Now, I've cleared all my variables, so you should do that beforehand anyway, if you're going to be using letters like we are here. So you can just go to Edit, Clear All Variables. All right. You can also go to Clear All. I cleared it before, so I'm not going to do it again because I just typed in that permutation matrix. All right, so this is a 4 by 3. So doing that, and we've got A, B, C, D, E, F, G, H, I, J, K, L. And yeah, sometimes it doesn't work. It's really frustrating. And even when I do variables, so what I might do, instead of using A, B, C, I'm going to use numbers just to show you. I wonder if it'll work for you. Didn't work for me. So if you got a question where you did have letters and it wasn't working, you can just use numbers, but remember what that letter represents for that number. So the number 1 would be A, number 2 would be B, C would be number 3, and so on. All right, so we can see if we look at first, so row 4 now become row 1. So my row 4 was 10, 11, 12, and you can see now it's in row 1, 10, 11, 12. All right, so that's how it's changed. All right, we also did it over here with the letters. Okay, so let's do a worked example. So a row permutation, if you're thinking, how will I know whether it's a row permutation or a column permutation? So this one here, we can see we're pre-multiplying, so the permutation matrix is first. So you should have these notes in your book. So here we've got it first, so it's a row permutation. So it's very important to note whether it comes first or second. You can also tell by the number of rows and columns. So here, this is our the matrix that's changing. It's a 4 by 3, and this is a 4 by 4. So obviously I can't do XP, is not defined. I have to do PX. So I've got no choice other than doing a row permutation for this one. All right, so let's fill in all our elements. So this one is in row 1, column 3. So row 3 moves to row 1. Then we've got, that didn't look like a 3. Let me just change that a little bit. All right, so then our next one is in row 2, column 1. So 2, 1. So it goes from row 1 to row 2. And then we've got 3, 4, so it goes from row 4 to row, not 1, row 3, and then the last one is row 4, column 2, so we go from row 2 to row 4. I shouldn't have these numbers mixed up, and you'll actually notice how if we did this in order, it goes 1, 2, 3, 4, which is super duper. All right, so we're doing the permutation first, so P times matrix X, just do a bigger X so we don't get our multiply and our X mixed up. And the order of my product matrix is going to be the same, so it's going to be a 4 by 3 again. All right, so row 3, let's highlight that one. There's row 3. The word the is now going to row 1, so the. Then we have, let's just change the color, let's do yellow. So row 1 moves to row 2. And then we've got row 4 goes to row 3. And then obviously row 2 goes to row 4. The fox was fed. That's great. I'm quite liking these examples. All right, so just understanding this change, extremely important. I would definitely have this in your bound book because sometimes you do have to create your own permutation matrix. You're not given one, so you do have to understand how it changes. So let's have a look at constructing a permutation matrix. So when there is a requirement to create a matrix permutation, an understanding of the position of the one elements allows for the construction of a permutation matrix. So that just means if you have an understanding of how they move, then you should be able to do your permutation matrix. It does require a bit of practice, and obviously you've got a bound book. Why not put an example in your bound book? All right, so for example, if column 3 is moved to column 1, then the resultant permutation matrix P would have a 1 element at 3, 1. All right, so column 3 goes to column 1, our element is, so our 1 is going to be at 3, 1. Now, if row 3 is to move to row 1, then we would have P1, 3. All right, so just making sure we understand whether it's a row or a column permutation, and also whether the permutation matrix is going to be first or second, or before or after the matrix being multiplied. All right, determine the permutation matrix P that would be required to change this matrix to this matrix. Okay, so determine the type of permutation. Have specific elements remained in the same row but shuffled positions. So let's have a look at where some numbers have gone. So this 21 has gone to here, and this 17 has gone to here, and then 42. So what we've actually got is a row permutation. So they've actually changed rows, right? So the 21, 17, 42 has changed from the first row to the second row. So we've got a row permutation. All right, determine the order of the permutation matrix. How many rows does the original matrix have? So we've got 3 rows, so our permutation matrix has to be a 3 by 3. Identify the row column changes to determine the 1 elements in the permutation matrix. So we're doing a row permutation, so if you ever get mixed up, you can always go back up here. Here's a row permutation. Remember, we did the permutation first. You could go back to the original notes back up here. All right, so when we're doing a row permutation, the permutation matrix is first. All right, so we've got a 3 by 3. So you can think about what that's going to look like. All right, so 3 rows, 3 columns. Now we've got only 1s and 0s. All right, so we know that. Oh gosh, what's going on? All right, so in our permutation matrix, thinking about your element, so we went from 1 to 3. Not to 3, we went to 2. Sorry guys. 1 to 2. When it's a row permutation, remember we do where it's switched to first. So we're going to have a 1 at P21. So row 2, column 1. All right, so we've got a 1 there. Then we can have a look at the next one. So let's highlight that in orange. So this row here went up here. So we had row 2 went to row 1. So we've got P1, 2. So row 1, column 2. And then our last matrix, our last row, so let's do that in green, didn't change positions. All right, stayed. So that means, hopefully you remember, so row 3 went to row 3. We've also, oh, why did I write a 2 there? Sorry guys, it should be a 1. That means that a 1 should go there, which we know when it doesn't change positions, you've got a 1 along your diagonal. So 0, 0, 0, 0, 0, 0. Now you can always check your answer, right? You can put this into your calculator. So let's just quickly do that. So 21, 17, 42, and I've just realized I should have done that my permutation matrix first, but that's okay. 22, 27, 46, 33, 15. All right, so row permutations go first. So we've got 0, 1, 0, 1, 0, 0, and then 0, 0, 1. All right, and just checking, and we got the right answer. Okay, so understanding what we, and I should just do the last one, P33, what is happening here, and then transferring that knowledge to the element is extremely important. All right, so let's have a look at some past exam questions. So a permutation matrix P can be used to change fears into safer. Now, things I would look at when doing this question, because you could do it on your calculator as long as the word, the letters all go in. If not, you can use numbers 1, 2, 3, 4, 5. It's just seeing whether any letters have changed, and none have. Oh, sorry. Let's rephrase that. Any letters have stayed in the same spot. Okay, so that would mean we would have a 1 along the diagonal. So none have changed none have stayed in the same spot. They've all changed. So I'm going to eliminate any options that have 1 along the diagonal. Okay, well, D isn't even a permutation matrix, so that's a bit unfair. That. All right, and A is also not a permutation matrix, so I can eliminate those two before I even begin. Now, thinking about whether it's a row or column permutation, we've got a 5 by 5 matrix as our permutation matrix. So that means, and my column is a 5 by 1. All right, so 5 rows, 1 column. So that means my permutation matrix has to come first. All right, so let's call it P times Q. All right, so just checking your orders. So P is a 5 by 5, Q is a 5 by 1. So that works because those numbers are the same. All right, so the number of columns in P is the same as the number of rows in Q. So our permutation is coming first, so that means it's a row permutation. So I'm going to look at how this F has changed. So F has gone from row 1 to row 3. So in my permutation matrix, because it's a row permutation, I'm going to do 3, 1. So I'm just going to see which matrices have a 1 in row 3, column 1. So not B, C does, and E doesn't. So the only possible answer is C. Now that doesn't, we didn't have to check any other ones, which was fantastic to see. So if we were doing that on our calculator, so we're going to do our permutation matrix first. I'm going to pause and do my permutation matrix. All right, there's my permutation matrix. They don't take too long to do, but if you mess up your position of your ones in a 5 by 5 matrix, is a bit annoying to do. All right, so we're going to multiply that by 5 by 1. Now, I don't think this is going to work. Let's just try it. I don't understand why it doesn't like. All right. 4, 5. So we can see the F, which is the number 1, has now gone here. Then our E, which was in position 2, should be here, which it is. Okay, so even though the letters weren't working, you can still use numbers to do it. So putting in all those permutation matrices would be very annoying. So do a process of elimination first. So it can't be A, can't be D, they're not permutation matrices. And then having an understanding of how they switch is good, because you don't want to be typing in then other permutation matrices just to check them. All right, but if last resort, just do it on your calculator. All right, it doesn't take too long to do. It's just probably takes less time to do it without your calculator. All right, Haley used the password, whatever that is, to unlock her computer. She uses a permutation matrix to scramble this password as shown in the product below. All right, so this is a row permutation, and it is what, a 6 by 6 matrix. So this is where it would be very good to have an understanding of how permutation matrices work. So I got, let's just do our position of our ones. Actually, let's see if there's nothing in our diagonal, which is very annoying. Okay, so we've got row 1, column 4. So this is a row permutation, so that means row 4 has gone to row 1. So in row 4 is the letter P, so that's now in row 1. So I can just cross off A and B. Now let's do the next row. So we're row 2, column 6. So we're going from row 6 to row 2. So remember, different order. Column permutations work differently. We're doing a row permutation now. So row 6 is a 2, and that's now going to row 2. So it can't be that, can't be that. So the only option is D. Now, you can't put these symbols into your calculator. You might be able to, but we can see the letters aren't even working. But you can put numbers in here if you want to. 6 by 6 matrix, time consuming, probably take you 2 minutes max, like probably take you 1 minute on average to put it into your calculator. Doing 1, 2, 3, 4, 5, 6, and then matching up the letters or symbols and then or numbers, and doing it that way is fine, but a lot quicker to do it without your calculator. All right, what else have we got? Matrix P and W are defined below. So if Pn times W equals asta, find the value of n. So what this means, and I kind of mentioned it before, but not in much detail, is when you keep doing your permutations, it actually changes. So when you think about it, we've got 5 letters here, so we can make up different words with those 5 letters. So we've got A-S-T-O-R, so we can change the position of those letters different ways. Now, we want this word to go back to its original word. And I kind of did something similar earlier with 1, 2, 3, but let's just have a look, doing it on our calculator. All right, I'm going to put the permutation matrix in. It's not going to be the same as the previous one, but I'm going to copy it anyway. All right, so we've got a 1 now here, and that means it's going to be a 0. Then we've got a 1 here, so that makes this one a 0. And then this is a 1. While I'm doing this, I'm thinking you could probably already have these set in your calculator, just in case you had a permutation matrix question on your exam. All right, so hopefully that's all good. All right, we don't know whether it's a, oh yes, we do. It's a row permutation because it's got the P there, but we would have worked it out quickly because of the order of the matrix. All right, so A-S-T-O-R, I really don't think it's going to work for us. Oh, it did. Wonder why those letters work and some don't. Okay, so when we did that, we get T-R-S-O-A. So that means when n is equal to 1, we get this matrix, T-R-S-R, T-R-S-O-A. My dog is being noisy in the other room. All right, then when n equals 2, all right, so all that means is we can take this same matrix and now we're going to do it to the power of 2. All right, so to the power of n. So we're letting n equal 2. And we get Sarot. All right, what do we get when n equals 3? And I wouldn't do this on an exam, but I'm using this as a lesson and how it works. So let's drag this down. So this time we're going to have a 3 here. So we have that R-T-A-O-S, R-T-O-A-S, and then n equals 4. Let's bring that down. So we're going to change that now to the power of 4, and we're back at asta. Now, I wouldn't do that on an exam, all right? Very time consuming. So, but you can apply what we've just learned here to any size matrix. So basically, we've got, let's call P. So P is a 5 by 5. So your value of n, so when n equals 1, that is the same. So your original matrix is the same as n equals 4. All right, so n equals 1 was our asta, n equals 4 was also asta, and you could think of that as being 5, so the number of rows minus 1. All right, so when we take away 1, all right, we get 4. And it's going to continue that pattern. So this was sorry, that should be 0. All right, so when we were starting off, I don't think we can do to the power of 0. Let me just see. Right. So when n is 0, we start off with Astor. And when you think about your sequences that we did during financial, all right, so n equals 0 is your original matrix. It's the same as n equals 4, so just your rows minus 1. All right, so n equals 4 is the same as n equals 0. So if we think about it like this, n equals 0, n equals 1, n equals 2, n equals 3. So that is the same as n equals 4. All right, so if we think of them as separate matrices, n equals 5, n equals 6, n equals 7. So if I did n equals 7, I should actually, let's do n equals 6 because it looks easier to see the word Sarot. So let's change it to a 6. All right, and we get Sarot. So any multiple of 4 for this one, so I'm going to add on another 4. So when n equals 8, I'll get Astor again. Let's just do it up here. All right, I'll get Astor. And think about what would be the next multiple of 4? 12. We get Astor again. Okay, so just look at your number of rows, take away 1, and then that tells you when your original matrix will appear again. I don't know whether we've got another question like that, but that's important to know. So if it was, say, this matrix here, right, this password will appear the same. So we've got 6 rows, so every 5th permutation will give you that original matrix. And then for this one here, every multiple of 4, all right, every 4th permutation. All right, and that's it. Bye guys.